Hi, this is John and I'm a student teacher for Jefferson High School in Lafayette, Indiana. I'm making this video to review and supplement knowledge regarding chemical nomenclature, specifically for inorganic compounds or compounds that lack carbon. There are a few exceptions to this, such as the polyatomic anions that contain carbon, such as carbonate. So to start, what is nomenclature? And why have nomenclature at all? So nomenclature is defined as a system of names or terms or the rules for forming these terms in a particular field. Uh, a type of nomenclature that might be familiar to people is binomial nomenclature in biology. So humans are referred to as Homo sapiens. In this nomenclature, the first word is the genus and the second word is the species. In writing, it's generally formatted in italics. So for the next question, why a nomenclature at all? For certain chemicals, it's more convenient to use common names like water instead of dihydrogen monoxide and table salt instead of sodium chloride. But too many and unique chemicals exist to give each a common name. In the Chemical Abstract Services Registry alone, about 164 million unique organic and inorganic substances have been identified in scientific literature so far. As such, chemical nomenclature was developed to systematically name chemicals that already exist, as well as chemicals that have yet to be synthesized or discovered. For practical purposes, the main advantage of learning chemical nomenclature is that the names themselves can provide information on the composition, structure, and bonding of a chemical. So when it comes to naming covalent compounds and ionic binary and ternary compounds, binary meaning composed of two elements, ternary meaning composed of three elements, it's important to be able to write the chemical formula given a chemical name and to write the chemical name given a chemical formula. Some general tips is to be able, it generally helps to memorize the names and chemical formulas of common cations and anions, cations being positively charged ions and anions being negatively charged ions. You'll notice in this list that most of your cations are elements. Most of your polyatomic anions are in the list of anions themselves. Another thing that's helpful to memorize are the names and symbols of common elements and their positions in the periodic table of elements. So noteworthy groups are 1A, which are the alkali metals, 2A, which are the alkali earth metals, and 7A, which are the halogens. These three groups tend to form ions. So this group tends to form plus 1 cations. This group tends to form plus 2 cations, because these two elements want to lose electrons to gain a stable electron configuration. And the halogens tend to want to gain an electron, so they tend to form -1 charges. Another notable group are the transition metals, generally from this blue block and some of these purple ones. Some of these elements tend to have multiple charges when they form cations, but some of them only form one charge. An example is this diagonal here. Silver always forms +1 cations, zinc always forms +2, and aluminum always forms +3. So it's 1, 2, 3. It's kind of a useful trend to memorize. Generally, memorization is the lowest order of thinking, but learning chemical nomenclature in this manner is analogous to learning basic arithmetic and math, such as your times tables. Knowing or recognizing the names of chemical compounds provides enough basic knowledge to discuss events involving chemistry. An example would be ammonium nitrate, which is NH4NO3. This was a chemical responsible for the Oklahoma bombing in 1995 in my home state of Oklahoma, and the 2020 Beirut explosion that happened earlier this year in the country of Lebanon. In this video, I'm going to play an explosion of ammonium nitrate. Ammonium nitrate was stored in a warehouse improperly with fireworks. This caused massive collateral damage and some civilian casualties as well. Unfortunately, the firefighters who came to the scene died thinking it was a typical fire, not knowing that an explosive was stored. Uh, this is generally one reason why we try to use as little chemicals as possible in the lab to try to minimize the damage to both people and to both equipment and personnel. So when it comes to naming chemicals, there's generally two big categories: ionic compounds and covalent compounds. I'll begin with ionic compounds. These are characterized mainly by ionic bonds or the presence of ions. They're generally concerned with formula units, and the chemical formulas are written as empirical formulas. Ionic compounds typically contain a metal. An exception to this is ammonium. Even though it's composed of all nonmetals, it acts more like an ion. So the example I'll use is sodium chloride. Here we have a crystal containing sodium ions and chloride ions. One thing you'll notice is that there's one sodium ion for every one chloride ion. The reason why I use empirical formulas is because you can have crystals of varying sizes. You may have a crystal containing 1,000 sodium cations and 1,000 chloride ions, or you may have even a larger crystal containing 10,000 sodium cations or 10,000 chloride ions. The important thing to remember is that the ratio remains the same. In other words, there's always one sodium cation for every one chloride anion. An image below is just an SEM image I found of uh, sodium chloride crystals. Generally, when you look at sodium chloride, you generally see like a perfect crystal. In practice, that might not always be the case. Most of the time, they'll try to form, a cube with 6 faces, but sometimes you'll get irregular crystal growth where you'll find members with many different facets, like this one right here. So when it comes to naming ionic compounds, generally you name the cation first and then the anion. Another thing to note for ionic compounds is to ensure that there's electroneutrality or a zero net charge. In other words, you want the total charge of your cations to be equal to the total charge of your anions. There's a need to designate how many of each ion there is in a chemical formula, uh, but it's implicitly stood that how many of each there are in the name. It's also important to take care when dealing with cations that have multiple and different charges. So the example I want to go over is iron 2 oxide and iron 3 oxide. As I stated before, if I just said FeO, you'd automatically know there's one iron 2 cation for every one uh, oxygen anion. But if I said iron 2 oxide, you would just have to implicitly know that there's one of these for one of these. There's nothing in the name that tells you how many of each there are. Also, I use these two examples because iron can form two different charges, a +2 or +3 charge. Depending on it's +2 or +3, you get different numbers of the oxide. So since this is a +2, this is a -2, you need just one of each. But for iron 3 oxide, you're going to need 2 iron 3s or 2 +3s for these 3 -2s. So you get +6 and a -6. For the next category, which are covalent compounds, these are generally characterized by covalent bonds. They're generally concerned with molecules, and they usually contain all metals for small molecules. Again, the exception is ammonium. So unlike formula units, for most molecules, you can basically count the number of each atom in the molecule itself. Here's one for carbon dioxide, and here's one for water. One neat thing about Molvu, which I'm using right now, is that generally use ball and stick to since it's easier to see how many of each atom there are and how they're connected. But most of the time, these molecules look more like this, just a bunch of balls overlapping. Same thing for water. So if you had a microscope that can really zoom in, water looks more like this. So when it comes to naming covalent compounds, so for binary or compounds that contain two elements, generally the more electronegative element usually comes second. But for all intents and purposes, compounds are named in order according to how they appear in the chemical formula. You also need to affix Greek number prefixes like mono, di, tri, tetra, and so forth, unless there's only one atom of the first element. So an example of this case is like carbon dioxide. You don't need to write monocarbon dioxide. Since there's only one carbon, you can just say it as carbon dioxide. But for the other case, like just H2O, you need to If there's more than one of the hydrogen, you'll need to designate it. So dihydrogen monoxide. So it might be a little bit difficult to memorize the nomenclature. So it helps to refer to a flowchart. You can find these if you just Google uh, chemical nomenclature flowchart. I just picked one since this one's pretty helpful. I can just go through it a little bit. So as before, generally compounds that contain metals, except ones containing ammonium, are generally ionic compounds. So you use the rules for ionic compounds here. If it's just all nonmetals, then you generally use the nomenclature for covalent compounds. I'm gonna reduce the image. If you want, you can pause the video and look at it in your own time. It's generally a very helpful guide. You probably won't have this when you're taking a test or a quiz, but if you just go through it, you can just kind of go through the chart and then figure, and it'll tell you how to name things. Anyways, thanks for watching the video, and I hope you do well in your test or quiz.